This is part 4 of lecture 8 of Elect 5300. In the last part, we kind of introduced the intuition of Bayesian estimation, and now what we'd like to do is make that intuition a little bit more formal by looking at the Bernoulli distribution that we discussed in the previous part and looking at the math. So let's just review. The Bernoulli random variable is a random variable that has values either 0 or 1, and the probability of x is equal to 1 is mu, and probability of tails is 1 minus mu. If I assign heads to be 1 and tails to be 0, then I can write it in this simple functional form, which enables me to do mathematical manipulation better than this tabular form, although this one is easier to understand. And so just as a reminder, when x is equal to 1, I get a 1 here and a 0 here, so I just get mu, and vice versa. So previously, we saw that given a set of training data, d is equal to x1 through xn, the maximum likelihood estimate of mu is the sample mean. Now, remember, things can be either 1 or 0, so we can count the number of 1s and the numbers of 0s. We can call that m and l, and of course m plus l is the entire set of times we have flipped the coin, or the entire size of the data set. That's n. And so the maximum likelihood estimate is just going to be expressed as m, the number of heads, divided by the number of heads plus the number of tails. Now let's look at this in terms of the Bayesian estimation. So to estimate the mu using Bayesian estimation, we have to assume a initial prior. Right, so we have this initial prior f of mu, and we want to generate a new prior f of mu given the data. And the way we do that by Bayes' rule is just we multiply by the likelihood of the data given mu, and then we divide by f of d. And this is just a normalizing factor, so we really don't have to worry about it. So all the action really takes place in those last two terms. So this is really where you need to pay most of your attention to. Now let's look at the way we can express the data in a simple, compact way. Before, we talked about just individual coin flips, x1, x2, x3, but if we again count the total number of heads, call it m, and the number of tails, call it l, right, then the likelihood function of m heads and l tails, we can multiply this out, but you just know, well, it's the probability of heads raised to the nth power times the probability of tails raised to the lth power. And so this is the likelihood of m heads and l tails given that the probability distribution is mu, or the probability of heads is mu. And so this thing here is what goes right here. So our data is m heads and l tails, and so that's the likelihood of the data. We're going to stick that inside here. And so what we'd like to have is we'd like to have f of mu have some form such that when I multiply it by this thing here, I get something that looks similar. And so I need to find the form of this, and I'm going to call that the conjugate prior. And so it turns out that there is a distribution over mu that has that property, and that's called the beta distribution. So the beta distribution is the conjugate prior for the Bernoulli random variable. In other words, it's a good description of the probability distribution function over mu if we assume that mu is unknown. So the conjugate prior here has this form here. Looks a little bit complicated. There's a gamma function inside here, but really this gamma function you don't have to worry about, because the only thing that really this gamma function does is make sure that when I integrate this whole probability density function over mu, that the integral integrates, the whole thing integrates to 1. Okay, so this is just a normalizing factor, and so this is really what's important. But now we can already see, right, if I take this and multiply it by this, then I'm going to get something similar. So let's take a look at this beta distribution in a little bit more detail. So again, this is the definition of the beta distribution from before, and mu here is constrained to lie between 0 and 1. So that makes sense from the point of view of our idea that the mu should be the probability of heads. And so the shape of this distribution here depends on two parameters, a and b, and these parameters a and b are assumed to be positive and real. They can be integer, non-integer, it doesn't matter. And gamma here is just the gamma function. But again, this one doesn't really matter. Now the shape of this distribution will depend on a and b, and so we call these hyperparameters, right? Because remember, mu is the parameter that we're trying to estimate. We're trying to estimate what the probability of heads is, or at least get a distribution over the probability of heads. And that distribution over that parameter is controlled by a and b. And so those are parameters controlling the distribution over the parameters. And so it's kind of one step higher than the parameters, so we call them hyperparameters. Let's take a look at what the beta distribution looks like for different values of a and b. So when a is equal to 1 and b is equal to 1, when I substitute that into here, I get 1 minus 1, or 0, and 1 minus 1, or 0 here. So this thing here just becomes mu to the 0, 1 minus mu to the 0, or this just becomes 1. And so remember, mu has to be between 0 and 1, so this is just a uniform distribution over 0 and 1. And so I don't really even have to evaluate this. It turns out if I do, it will be 1. But anyways, the thing has to be a probability distribution, so it's constant over this interval of 0 to 1, so the value here has to be 1. So that is a pretty good description of the idea that, well, I know the probability is between 0 and 1, but I have no preference for any particular value inside that interval. And that's what we started out our intuitive example with, and we can achieve that using this distribution. Now, if I change the parameters a and b, let's say a is equal to 2 and b is equal to 3, then you can see I get this kind of humped thing here, right? So a is equal to 2, I get mu to the 1, right? So that kind of gives me a linear slope down here. And I get 1 minus mu squared, right? So 1 minus mu is going to be 0 at mu is equal to 1, and 1 minus mu squared is going to be like a parabola. So I'm going to get a little quadratic down here. So I get something linear down here, I get something quadratic down here, and so this thing kind of has to come up and then eventually come down and be linear here. And so you can kind of see that the peak value here is going to be a little bit shifted over toward the origin because I've got a stronger power down here. So when I have a stronger power down here, it's going to kind of push the peak over here. So now if I have, on the converse, a is equal to 8, then I have the 8th polynomial, mu to the 7 over here. So I have a 7th order polynomial here pushing this down here. I have b is equal to 4, so I have 1 minus mu to the cubed. So I get a cubic here. So I get a 7th order polynomial here, a cubic here. And so this is going to be stronger here. It's going to push it down further, and the peak is going to end up somewhere over here. Now, like I said, a and b can be any reals. Doesn't have to be integers, and so here's just an example of that. When a is and b are less than 1, then I get something negative, right? So here, if a is equal to 0.1, I get mu to the minus 0.9, right? So it's 1 over mu to the 0.9, and so that kind of goes to infinity at mu is equal to 0. And when b is equal to 0.1, I get a 0.9 here as well, and so that goes to infinity here, and then it drops down like this. Okay, so I can get a whole range of different distributions here, but probably for the coin flipping experiment, the ones here, these three are going to be the more relevant ones that we're going to be looking at. So looking at this kind of thing, what are some of the things we notice? Well, if we look at the mean value here, we can see that the mean value shifts toward the origin when B is bigger than A, right? And it shifts toward 1 when A is bigger than B. And the other thing we can see is that you get a pretty broad distribution over here when A and B are relatively small, also in this case here. And it seems to be a little bit sharper distribution here when A and B are larger. So if we go back one slide, we look here, and it turns out that if we can look up in any probability textbook, or you could try to integrate it out if you wanted to, the mean of mu under this distribution depends on A and B, and it's just given by A divided by A plus B. And so if, maybe we can rewrite this one as 1 divided by 1 plus B divided by A, right? And so if B is bigger than A, right, then I get 1 plus something bigger than 1, right? So this is going to be bigger than 2, so I'm going to get something smaller than 1/2, right? So if B is bigger than A, I'm going to get something smaller than 1/2, which is consistent with the thing here. B was bigger than A, I got something smaller than 1/2, and if B is bigger than A, if A is bigger than B, then I get something bigger than 1/2. And so that's, if A is bigger than B, then I get something here less than 1, and so this whole thing will be less than 1/2. Oh, sorry, I mean, this will be less than 2, and so this whole thing will be bigger than 1/2. The variance here is going to go as AB divided by A plus B squared, A plus B times A plus B plus 1. And the thing to realize here is that this is just a second order polynomial, but here I have a third order polynomial, right? I get something like A cubed here. So I have second order divided by third order, and so when A and B get bigger, this thing will go to 0. And that is capturing the idea that the variance here is getting smaller for larger values of A and B. Okay, so the key message to take home then is this beta distribution has a functional form that looks kind of like the likelihood. It generates these distributions over mu that look reasonable for modeling the probability of coin flips. And it depends on some parameters A and B. Now let's look at the probability, the posterior distribution for mu, assuming that we've observed some data which consists of M heads and L tails. So remember that we really don't have to worry about the normalizing factors, those gammas, because we just have to, in the end, those are just going to turn out to be something that makes sure that the probability distribution integrates to 1. So the probability distribution over mu given A and B, these are determining my prior parameters. So for example, A is equal to 2 and B is equal to 2 will give us what we started out before. A is equal to 1 and B is equal to 1 will give us what we started out before, the uniform distribution. Right? And then I observe the data, let's say M heads and L tails, right? And the posterior distribution is just the product of the prior and the likelihood. Now, the prior has this form over here. This is from the beta distribution. The likelihood has this form here. And then what I can do is I can just combine the coefficients of mu to get mu to the m plus a minus 1. And to combine the coefficients of 1 minus mu to get 1 minus mu to the L plus B minus 1. And so if we look at this, this has exactly the same form as this, right? It's just mu raised to some power and 1 minus mu raised to some other power. And the parameters are just determined by those A and B parameters in L, M and L. So the posterior then has exactly the same form as the prior distribution because we've used the conjugate prior, and so therefore I already know what the normalizing factor is because this has to be a probability distribution. It looks like a beta function, so I know that, well, for the beta function it's just gamma of this, m plus a plus l plus b, divided by gamma of this times gamma of this. Okay, so I already know what these normalizing factors are without even having to do any kind of integration or anything that might be suggested in the formulas. So the key difference then between the posterior and the prior is that originally I started out with hyperparameters a and b, and now I've increased them to a plus m and b plus l. And so the hyperparameters a and b in the prior can be interpreted then as some kind of assumption about the expected number of ones and zeros in a virtual experiment, right? So this kind of gives us some kind of indication of how many ones and zeros I might have, because if I actually observe ones, then I add it to a, and if I actually observe zeros, I add the number of zeros to b. The other thing to recall is that, well, as we collect more data, we should be getting better and better estimates of mu. And so what happened here is when we collected data, either at least A or B will increase, right? Probably both of them will. And so remember what we said before. We said that, well, the variance here will get smaller the larger the values of A and B are. And so that indicates that as we collect more data, we're going to get more certain about our parameter values, or we're going to decrease the uncertainty. Now remember that we don't necessarily want to have the probability distribution over mu. Right? What we really want to do is predict what's going to happen to x, right? So we're only interested in mu insofar as what it tells us about the probability of heads or tails in x. And so let's take a look at the probability distribution function over x, right, given the data d and our original assumption about the probability distribution over mu, which was determined by a and b. So the probability that x is equal to 1 given the data is just the probability of x is equal to 1 given mu times averaged over all possible values of mu, where this probability distribution here function is determined by the data. Well, the likelihood function f of x equals 1 given mu, this is just the probability that x is equal to 1 if I know mu, and the probability that x is equal to 1 is just mu. So this thing here is just mu, and so if I replace that, I get this. This is just the expected value of mu given d, and so if you remember, given d, the mu has this probability distribution function, and so I can go back to the previous slide here, and I know what the expected value of mu is for these parameters, just a divided by a plus b. But now with the data, the a is replaced by m plus a and b by l plus b. And so now the expected value of mu given d is just m plus a divided by m plus a plus l plus b. Conversely, I can do the same thing for x is equal to 0, or I can just take 1 minus f of x equals 1 given d. Right? And so if I add these two together, you can easily verify that I'm just going to get 1, right? Because I'm going to get m plus a plus l plus b on the top and on the bottom. One of the nice things about the Bayesian estimation is that if I get a lot of data, right, then basically I start trusting the data, right? Because I have so much data, whatever I believed before, I should just trust the overwhelming amount of data that I get. And so when m and l go to infinity, right, then you can see here, let's take a look at this one here. When m and l go to infinity, then this becomes much bigger than a. These two things become much bigger than a and b, and so this one goes to m divided by m plus l, which is exactly the estimate of mu, which was given by maximum likelihood. And in fact, we can prove that for any finite data set, the posterior mean of mu, this thing here, always lies between the prior mean and the maximum likelihood estimate. So the prior mean, remember, was just a divided by a plus b, right? So that's this. The maximum likelihood estimate is m divided by m plus l. And this is always in between that. Right? And so if you want, you can prove that yourself. But intuitively, what that means is that initially I have some distribution over the mu. Right? So maybe I have a prior value here, a divided by a plus b. And as I collect more and more data, right, my maximum likelihood estimate might be here. Let's say m divided by m plus l. And as I collect more and more data, the estimate is going to start shifting from this point here down to get closer and closer to this point here. So if a and b are very large compared to m and l, it's going to be closer to this. But if m and l are large compared to a and b, it's going to be down closer to this. Finally, I'd like to point out one nice thing about the use of the conjugate prior, and that is the fact that it allows us to do sequential estimation. So if you remember when we looked at maximum likelihood, the maximum likelihood estimate is m divided by m plus l. And so in order to estimate the probability of mu, what I have to do is I have to do all my experiments and then count the number of heads and divide the number of heads by the total number of trials, m plus l. Now, you probably heard this term big data. Everybody's saying we live in this era of big data. And so what that means is that we have a lot of data that we need to kind of assimilate or combine. And so because we have so much data, it becomes very, very computationally intensive to handle this data. And so what we'd like to be able to do, let's say if we've gone on the internet and we've downloaded, let's say, 100 million pieces of data and we've processed them, if I come back the next day and I find out, well, somebody has, created another, let's say, 1,000 pieces of data, I want to take that into account, right? And so one thing I might do is, well, I already downloaded like 100 million pieces of data, and so I'm going to then take that extra 1,000, add it in, and I'm going to have to again process about 100 million or 100 million and 1,000 pieces of data in order to get my new estimate, let's say my new estimate of the mean or something like that. That's going to be a lot of work just to take into account 1,000 new pieces of data. And so the question is, well, can't we somehow just update our estimate to take into account the new data? And the answer is, using this kind of Bayesian estimation, we can do that. And so this is all because of the fact that the conjugate prior and the prior have the same form, right? And so now if I've taken into account some pieces of data, right, then I get a new posterior, but the new posterior actually has the same form as the old prior. right? So I can actually use the posterior as the new prior and then just incorporate the new data as it's observed. Right? So this leads to a sequential algorithm that I've kind of shown over here. So suppose that we have a prior distribution over the probability of heads, where for some reason I believe A is equal to 2 and B is equal to 2. That will give me this kind of quadratic function here that peaks at 0.5. Now, if I observe, let's say, 1 head and 0 tail, so I observe 1 coin flip, then my likelihood function is just mu. Right? So the likelihood function is mu, and so that's just a line with slope 1. Now, in order to take into account the new data, I'm going to get a new posterior distribution. I'm just going to take this and multiply it by this. So you can see here I get a linear thing here times a linear thing here. It's nearly constant over here, so I don't really change that much over here. So I get a square term down here on the bottom, and it comes down linearly like this. And so this is also described just by taking A plus M, which is 3, and B plus L is equal to 2. But now I have this posterior here, which exactly have the same form as this one here, except the parameters have changed, right? So now if I have a new piece of data that comes in, what I can do is I can just take this one, put it over here, and let's say the next time I have something like tails, right? So if I had something like tails, then the likelihood function would look like this. It would be 1 minus mu, and when I took this and I multiplied it by the new prior, which would be this thing, you can imagine that I would get something that's kind of similar to this over here, and then kind of comes down like this on the other side, and this you can imagine would be symmetric over here. And now I can take this one, put it back up here, and then flip the coin again and take into account new data. And so now, instead of having to revisit all the old data, what I find is the prior captures all the information I need about the old data, and I can just throw that old data away. I don't have to look at it again because all that information is captured in those hyperparameters. And this is the big advantage now of these kind of Bayesian techniques, especially in this era of big data. It leads to these sequential, or what we call online estimation algorithms. Okay, so we've gone through this example of Bernoulli distribution in fairly good detail. Hopefully that gives you more concrete ideas of some of the concepts we talked about in the previous part. As we move forward, I'll show you some more examples of Bayesian estimation for other kinds of distributions.